All right, thank you for coming back to page 2. We are going to be doing some more examples of L'Hopital's rule today to find the limit of each of these 6 problems here. And again, we always start by trying to substitute in. So when we substitute in x equals 0, this is going to give us the sine of 0 over 0, which is 0 over 0. So now we're going to try L'Hopital's rule, which means we're going to do the derivative of the numerator and the derivative of the denominator. The derivative of the numerator, the derivative of sine, is cosine 5x times the derivative of the inside, which is 5, all over the derivative of the denominator, which is 1. And now we sub in again. Sub in again, and we're going to get the cosine of 5 times 0, all of that times 5. The cosine of 0 is 1 times 5, 5. That limit is 5. Take a look at this next one. Let's sub in. When we substitute in a pi over 2, we have 1 minus sine pi over 2 over 1 plus cosine of 2 times pi over 2 is just pi. Sine of pi over 2 is 1. So we'll have 1 minus 1, 0, over. Cosine pi is negative 1. So we have 1 plus a negative 1, 0. All right. So we have our indeterminate form. So let's go ahead and do L'Hopital's rule then. And we'll do a derivative. The derivative of 1 is 0. Don't forget your limit here. So we have 0, and then the derivative of a negative sign is going to be negative cosine x. On the bottom, the derivative of that 1, 0. And then the derivative of this cosine 2x, that's negative sine 2x times a 2. All right, now, we really don't need this first 0 here, so I'm going to go ahead and take that out. A little bit easier to see now that these two signs are both going to turn positive here. And we're going to go ahead and sub in. We can sub in that pi over 2, cosine pi over 2 over 2 sine pi. Uh-oh. We have 0 over 0 again. So do L'Hopital's rule again. And we'll do the derivative of cosine here. That's negative sine. And the derivative of this sine 2x times 2, or 2 sine 2x, is going to be 2 cosine 2x times another 2. Now sub in again, and we'll have negative sine pi over 2 over 4 cosine of pi. Sine pi over 2 is 1, so this is negative 1 over, down here, 4 times cosine of pi. Cosine of pi is negative 1, so we have negative 4, which is 1/4. There's your limit. Oops, I hope you can see it. I don't know if I got you off the screen here. I'm sorry. There we go. All right, it's pretty straightforward. It's taken me a while to talk you through this, but really this is just a lot of multiple derivatives. And you keep subbing in, and if you get a 0 over 0, then you do another derivative of the numerator and denominator separately. So let's take a look at this one. Again, if we sub in first, let's see, we're going to have 2 squared, which is 4, minus 4 times 2 is 8, plus a 4. All right, there's 0 in the numerator. Denominator, 2 cubes, 8, minus 2 times 12 is 24, plus a 16. Oh, another 0 over 0. So let's go ahead and do the limit as x approaches 2. We're going to do L'Hopital's rule. Do a derivative of the top. So 2x minus 4. Derivative of the denominator. 3x squared minus 12. Sub in again. 2 times 2, 4 minus 4, there's a 0. 2 squared is 4 times 3, 12. 12 minus 12, another 0. So we'll do L'Hopital's rule again. Derivative of 2x minus 4 is 2. The derivative of 3x squared minus 12, let's see, that's going to be a 6x. Sub in the 2, and we'll get 2 over 12, or 1/6. So again, you have this indeterminate form of 0 over 0, and we just keep doing derivatives until we can substitute in the number and we don't get a 0 over 0. Couple more here. Looking at number 5, the limit as x approaches 0 from the left of tangent x over x. All right, substitute in. This would be the tangent of 0 over 0. Tangent is 0, 0 over 0. All right, let's do a derivative. The limit as x approaches 0 from the left. The derivative of tangent is secant squared over 1. Now we can just plug in, and we'll have secant squared of 0, which is secant of 0, that whole thing squared. Secant is 1 over cosine. And cosine of 0 is 1, so we have 1 over 1 squared, 1. All right, now look at this. The difference between these two problems. This is the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right. Did we ever have to deal with identifying left and right in small negative number, anything here? And no, we didn't. So this one is going to be exactly the same thing. There's no difference then when you use L'Hopital's rule with left and right issues. So this limit is 1, just like over here. Oh boy, this last one looks nasty. And don't get freaked out about it because it's got this integral in here. We're still going to go the same thing, same process. So we're going to sub in the 1, which means this looks like the integral from 1 to 1 of dt over t, and 1 cubed minus 1. All right, this is asking you to find the area from 1 to 1 underneath this curve. Well, it's still 0 over 0. All right, so now L'Hopital's rule, we're going to do a derivative of the numerator and the derivative of the denominator. Don't forget that limit notation. Numerator is going to be the derivative, so d dx of the integral from 1 to x of dt over t. Oh, you know what? Let's change that a little bit. You might want to think about this one instead of dt over t. It might be easier for you to think about it as 1 over t times dt. And the denominator, the derivative of this x cubed, would be 3x squared. Okay, now you got to simplify. This derivative of an integral. Remember when we did that, that's the first fundamental theorem. When you do the derivative of an integral from a constant to a variable, that variable just gets plugged in for that t. Oops, sorry, I was thinking t, but should have written an x. 1 over x, and then times the derivative of that upper bound, so times a 1, all over 3x squared. Okay, now can you substitute in a 1? Sure, we get 1 over 3 times a 1 squared. That's 1/3. All right, there's some examples for L'Hopital's rule with the indeterminate form 0 over 0. There are other indeterminate forms, and we will investigate those on page 3.